Okay, I think it's recording already. Welcome back from the break. Now we will analyze phase transitions. The kind of phase transitions we will see here is first order phase transitions, where, of course, some quantities are kept constant, no? During the phase transition. Give me an example of a first order phase transition you have seen in your life. I think you have seen many, but tell me one. Ice melting. What do you think happens when the ice melts? Expands. Expands freely, no? The water just fill the glass or whatever, or if it's on the floor, it just spread everywhere. And then what can we conclude from that? There is a sudden jump in the volume, no? So there is a discontinuity. The volume of the ice suddenly change abruptly to become the volume of the water much. And if the water evaporates, the volume of the water suddenly becomes a huge, a large volume, low density, with the same mass, of course, because you have the same mass. And what else happens during this phase transition is illustrated in this diagram. You have solid phase here, liquid phase, and gas phase here. So something which this diagram is showing is that when, let's put it this way. Let's assume you have an ice at temperature. What is the lowest temperature you have seen in Europe? You're from Europe, huh? Or anywhere, Beijing, Japan, Tokyo, I don't know.
Seen?
Well, which you felt, I mean,
-5, 6 degrees.
-6 degrees. Let's put -6 degrees Celsius. In Celsius, no in absolute temperature. If I hit this guy, I want to calculate the change of internal energy of this. Then, of course, I will do approximately mass of the ice, heat capacity of the ice, change of temperature until reaching 0 degrees. No, this change of temperature will be final temperature is 0. Initial temperature is -6, so it will be +6. In Celsius, Kelvin, it doesn't matter because the changes of temperature in Kelvins are equal to the changes of temperature in Celsius. Okay? But then what happens when you reach 0 degrees? You are here and you continue input heat. You have the ice here, the piece of ice, and you input some heat. Does the temperature change? Not for a while. Why? Why is that? Actually, why is the way Hong Kong people reply the phone also? Why do you think? Why Shama? ¿Por qué? Porque you speak Chinese, actually? No. Nobody here is Chinese, I think. You are Chinese? Okay, you are the only one here. Everybody else, you are from Portugal, South Africa, and the other side for where are they from? Well, anyway, it doesn't matter. Later you can tell me. Anyway, let's come back here. I increase the heat. I continue inputting heat here. And then the temperature will not change because this heat is being used for changing phase, for a phase transition. So the ice, 0 degrees, will convert in water of 0 degrees. The initial water which form, and in between there will be a mix of the two phases. And this mix, whether there is more water or whether there is more ice, it can be seen in the phase diagrams. And these phase diagrams are not exclusive of water. Many materials have phase diagrams. In metallurgy, people use phase diagrams for analyzing materials, and in such a case, there are many phases. In advanced material science also, but however, they also consider second-order phase transitions where there is not this kind of discontinuities, or where the symmetry arguments of the system define whether you are in a phase or the other. But we will not see that case. I will just mention them crossing by. Superconductivity itself is a phase transition, for example, but this second order and is analyzed via spontaneous symmetry weakling, which is a phenomenon we will not see here. Ferromagnetism also is some kind of phase transition, which we will not see here because it's some kind of outside the scope of the class. But you should know that these are phase transitions. The material changes suddenly from being non-magnetic to being fully magnetized, for example. And superconductors, they change from not allowing the current to flow freely to suddenly allowing the current to flow without any resistance. Even if you remove the voltage, it continues the current for many, many years as far as you keep the condition. Phase transitions have something in common, no matter they are first, second order. Free parameters. You can control some parameters for controlling the phase transition. And let's develop the intuition of this because this is very important. Intuition is more powerful than knowledge, actually. Because when you have intuition and you want to get new knowledge, you say, this makes sense. This is right. This is wrong. This doesn't make sense. These kind of things. We talked about this before, but let's go again to the case of the tank with water. Tank with water. If I increase the pressure, of course, it's more difficult for the water to evaporate. We know that. But the pressure is one of those free parameters I can control externally. The temperature is another free parameter I can control. And this has applications not only in material science, not only in this kind of thermodynamic analysis, but in analysis of collective behavior, where people use quantum fields, for example, for modeling the collective behavior of people. For example, you can use quantum fields. And some external parameter, tell me one parameter which I can control in this room, which will affect your behavior collectively. Imagine you are atoms here, bunch of atoms, the temperature. What can happen? What happens if I increase the temperature of this room to 40? Yeah, well, let's assume that you are a rational person, you're sitting here, and what will you do if the temperature is 40 degrees? Sweat, and beside that, you will leave the room, most likely. You say, it's too hot here, I don't want to be here. That's collective behavior, and even in collective behavior, these applications exist, where you can control the externally, the free parameters for detecting whether there is a phase transition. There are social phase transitions also. The pandemic itself, the propagation of a virus, is a phase transition also. Social phase transition, but phase transition at the end. When the fishes operate collectively or not, that's a phase transition also. But that's the kind of second order phase transition we will not see here. Well, I can explain whoever is interested in future or later or so, I can explain that. Here, we reduce to first order phase transitions, and then the water starts to melt at 0 degrees, and when you are here, everything became water already, but at 0 degrees Celsius. Still, of course, what is discontinued? The volume, because you put not an iceberg, an iceberg in a big enough pool. The iceberg will occupy its volume, but when it melts, it will occupy the volume of the pool. So, of course, the volume of the water will be much larger than the volume of the ice itself. Because it's a spread, no? So this discontinuity exists, and then the change of, or let's say the analysis, the thermodynamic analysis, you need to incorporate something called latent heat. This is the latent heat, which is the heat that the object absorbs without changing the temperature during the phase transition process. Now, in liquid, you continue inputting heat. It will reach a temperature, in the case of water, will be 100 degrees. 100 degrees here at atmospheric pressure. And then what will happen? The first, there are early stage molecules escaping. The larger, the more heat you input, more molecules start to escape until everything becomes gas, a vapor. And then what happened? Let's put here, I put a tank of water here and I input heat. What will happen? It will vaporize, and then what will happen with that water will spread on the room completely. There is a discontinuity in some thermodynamic properties. The volume is discontinuous. But at the same time, the first gas which is created has 100 degrees. 100 degrees. Just boil water, and the first gas which will emerge is 100. Now let's assume you can trap this gas. You close the oven or whatever, or the glass or whatever you are heating, and then this gas will start to increase the temperature also. Well, after it changes the phase, after it becomes, and then temperature becomes higher. That's how it works. Then during this process of transition, there is no change of temperature. This is also called latent heat. Calor latente. Calor latente. I don't know how to say in Chinese that one, but latent heat. I don't know. How do you say very hot in Chinese? Hanra? Is Hanra? You should know. No, you don't know. Okay, anyway. Yeah. Han something. It should be Hanra, because Hanlan is very cold, no? Oh. Yeah. Hanra, yeah, I was right, no? Hanra. Now let's show another phase diagram, and you will see what I'm talking about. This one is better. This is the diagram pressure volume. Many substance, many elements, or many liquids or whatever, or materials, they behave in this way. Then, for example, of course, large volume, this is the gas phase. This is the phase of coexistence, and this is the liquid phase, I should say. Then when it comes here, you can see, during this period, this is an isothermal. There is the volume here is much different to the volume here, becoming gas. But during this transition, there is an input of heat, of course, and this is called latent heat. If you reach this point, this is a critical temperature. And after this, the phase transition is not first order anymore, it's second order. We will not see the second order phase transitions. I remember when I studied thermodynamics for the first time, that those areas were mysterious for us. After, when I studied quantum field theory, condensed matter systems, I understood more these kind of transitions, which doesn't involve this kind of discontinuity. So these diagrams, I just want you to take into account that this is a phase, this is another phase, and this is the coexistence phase. And then, for example, if you are here, the location along this isothermal here, which will determine whether there is more gas or more water. And you can find the fraction of water or the fraction of gas which is available in some system. Because if you know that the system is here, and you know this distance, and you know this distance, you can know the fraction. This kind of problems exist, but we will not see those problems here. But I want you to know because this is part of the course, advanced course of thermodynamics. It will require deeper training from your side, which is in a few sessions you cannot do. And this is the other diagram. Let's say these are projections in different planes. This is the diagram pressure temperature. Actually, it's a three-dimensional diagram. It's pressure, volume, temperature. But when you project in the plane pressure temperature, it looks like this. You have the triple point where the three phases coexist, vapor, liquid, and solid. This will be, for example, the ice. This will be the water, and this will be the vapor of water, for example. And this is the triple point. This is the critical point. So the triple point of water, I forgot what's the value, though. Nobody memorized these things, so it's on the tables, it's on the textbook. There is a critical point also. So what I want to emphasize is that when there is in this case, of course, it's more difficult to visualize that the temperature remains constant during a phase transition, but it's something which certainly happens. So this is the projection in another plane. And that's it. So now you know phase transitions. Then let's put an example. Before going to the thermodynamic cycles, I'll put you an example to see what is your capability of reasoning now that we did that problem. Let's go to the same problem of the tank. Always a tank. No? Not so original. Why? Always a tank, professor. It's for you to get familiar with the problem. Again, liquid. The liquid is at 40 degrees. Or how much did we say last time? How much was it? 20. Okay, let's put the same values better for. Let's put 20, that the water is at 20. But now let's put not the iron, let's put a piece of ice, which is solid. Of course, the ice is floating in reality. The ice is like this. If we have time today, we can start to study buoyant force and see, because we have to jump to Bernoulli and these things. But you should know there is a fraction of ice deep below, and a fraction, and this picture is wrong because actually the part which is below the water is larger. It should be larger. You will see that when you see an iceberg, let's talk about the Titanic, for example. What was the catastrophic issue in Titanic? Is that the iceberg, it looks monumentally big outside, but if it's monumentally big outside, is much more monumentally big inside the water. Okay? And we will calculate in future what's the percentage of ice below the water. And you will see, oh my God, that's why the Titanic sank, better, it's fast. Why the Titanic sank? Because of that, because precisely it was like having a huge building in front of you. You know how massive is an iceberg? I mean, the inertia which represents an iceberg. There was no way to survive that thing. But by the times, this is a parenthesis, the science of materials was not developed. So the material of construction of the Titanic at low temperatures was fragile. Now our materials are better. If it happens the same, they will not sink for sure. In addition, because they will not be confident, they will have enough boats for saving people. But independent of that, the material should be resistant enough for having a crash or something. That didn't happen. The Titanic opened and it sank. And part of the reason is at different temperatures, the materials behave different. A material which is very strong at ordinary temperature can become very fragile at certain temperatures. And that's important for construction of planes, for example. The airline companies or the companies which design the planes, when a plane flies very fast, the surface becomes very hot. The friction of the air, it will make, and sometimes it has to land in a very cold environment. So this kind of sudden changes of temperature, the planes and the materials should be able to sustain the same behavior. That was a parenthesis. I like to mix the things like that because it's more interesting. But let's put it this way. So now we have this water, we have the ice. Now let's put the ice at minus 10 degrees. The temperature of this ice, I took from the bridge, it was minus 10 degrees. Then how do you analyze this problem? We analyzed this problem before, but let's analyze it now. Now there is a phase transition in between. There is a phase transition. Then what's the first thing you calculate here? Of course, the heat that the water, let's say the heat that the ice receives is minus the heat of the water. The heat of the water, we know how to calculate because the change of internal energy of the water is the mass of the water, heat capacity of the water, change of temperature, assuming that the heat capacity is constant. For the ice, we have to calculate mass of the ice, heat capacity of the ice, between 0 minus 10. We have to calculate this change first. And then there is the change, the heat due to the latent heat phase transition is the mass of the ice multiplied by the latent heat. The latent heat is on the tables in the textbooks. You can find anywhere. Latent heat. Okay? And in addition, finally, remember that for the water, let's finish the one of the water, mass of the water, heat capacity, final temperature minus initial temperature, which is 20. The water behaves normal, the water doesn't change phase, but the ice change phase. So now it becomes liquid. So you have to add the heat after when it becomes liquid. So it's ice, water, let's put, for distinguishing from the water, the original water, it will be the mass of the ice because the mass doesn't change. Ideally, it doesn't change. Heat capacity of the water, because anyway, it's water, and we are assuming that the heat capacity of the water doesn't change with the temperature, which is not accurate, but still approximation. Final temperature minus 0 degrees because it comes from 0. So you have final temperature again is the only unknown. And later you will solve this. I want you to solve it by yourself because it's not difficult. You will just add this plus this plus this plus this. It's equal 0. It has to be equal 0. Assuming all these heats is equal 0 and you solve the final temperature. And bingo, you have it. So what's the difference between this problem and the previous one we did? Is that now there is a phase transition for the ice. Phase transition for the ice. Right? Okay, nice. It's understood, no? It's clear. It's so clear that I will be surprised if somebody doesn't understand, it's because they are not watching here. They are watching the games or laptops or so. This class behaved particularly well. I like this class. We can do these recordings here. But when I teach the other class, it's a little bit disaster. And then I cannot do these recordings, unfortunately, no, because it would be nice for them to receive these recordings in future. Anyway, now let's complete the framework of thermodynamics. Now that we understand that there are phase transitions. Now, of course, if there is a vaporization, of course, now you have to do the same exercise. There is a latent heat of vapor, blah, blah, blah. In the exam, I will ask this kind of questions. Actually, when is the exam? Do you remember? Is next week, or I have to check the calendar. Is next or next? Anyway, we can arrange, we can negotiate You don't have to become angry now. We can negotiate the dates, no problem. Because you have also homework and so on. Then, when you are in your houses at night, why do you need to close the curtains? Especially, let's say, for example, you are in a hotel, let's assume it's cold outside. Well, not so cold, actually. But people say close the curtains. Why is it important to close the curtains, actually? Outside, it becomes cold, and then the air, anyway, especially in Macau, Japan also, where the air is humid, there is a lot of vapor here. Then, of course, you will see some condensations on the. Of course, this your room will become very, very, very cold, and you can get a disease, right? That's so. There is a phase transition actually on the windows. You have seen that many times. Condensations, which also you remember the accident of the Apollo 11, no? Apollo 11 had to come back. There was condensation in their devices, and they almost have some issues because of that. Well, that's a case where phase transitions occur. Something I have to remark also, why in summer in Macau particularly, and in Tokyo and in Japan in general, why in those seasons you transpire so much? Why you are like sweating like crazy? Also, that's partially correct, but there is another issue. Is that there is so much humidity in the air that the water in your body cannot escape. Then it remains with you, no? But if the air is dry, if the humidity is low, any water you have in your body will evaporate. Yeah. The difference, the gradient, no? This is some kind of potential, the gradient of concentration. So I will close by this thermodynamic part with the cycles. Look at this image. This is again the piston, okay? Doing work, expansion, coming back. This is a thermodynamic cycle. And the thermodynamic cycles have a series of steps for it to occur. This is an isothermal expansion. This is just an example. Isothermal expansion is that there's a reservoir inputting some heat and this expands. And it's isothermal because it occurs at constant temperature. Then after, this adiabatic expansion, so it means there is no flow of heat on the borders. Then after, there's a compression at constant temperature. And then after, the adiabatic compression, which is, this cycle is called Carnot cycle, actually. Carnot cycle, and it's an ideal cycle, and the diagrams are illustrated here. In the pressure volume diagram, it looks like this. The heat enters, the heat goes out. Well, this is an ideal process, but you can see that even in this ideal process, you cannot use all the heat for generating work. Part of the heat which enters goes out. And that's why not even the most ideal machine in this world can operate 100% of efficiency. But understanding what is the efficiency of Carnot help you to understand, okay, what do you have to do for improving the efficiency of your machine? Another issue is that the larger is the difference between the temperature high and the temperature low, the larger the difference is, more irreversibilities occur and the entropy increases more. If you don't want the entropy to increase that much, you have to approach this temperature to this, but it will be like doing nothing. It's almost thermodynamic equilibrium. Now, in thermodynamics, you will see some diagrams. The thermodynamic diagrams are just approximations to the reality because the diagrams, they are just telling you portions of the thermodynamic equilibrium. Let's say, for example, in this diagram, The fact that you know this padding means that you know the conditions here, the conditions here, the condition here. But this is approximating a real machine. You don't know what are the conditions between these 2 points. You only know that here happens this and here happens. In between what happens, I have no idea. So I think when you see thermodynamic diagrams, sometimes those are idealizations of the reality. So this is what we have seen. Heat enters, go outward, and heat has to be thrown away. Otherwise, there is no cycle. And this cycle has an efficiency somebody calculated for us. And this is the efficiency, because in this kind of cycles, this ratio between the heats of the hot part, the cold part divided the hot part, the heats, is equal to the ratio of the temperatures. Then the Carnot cycle has this efficiency, 1 minus the temperature of the cold. Let's put here. This is temperature hot, temperature cold. This is the machine. This is the work. Hot, cold. Right? So what this is telling you is that actually this is better to put in absolute value because the heat can be positive or negative. Then they are telling you that the ratio of these 2 guys is equal to the ratio of these 2 temperatures. And then when you replace that in efficiency, remember, how do you find the efficiency of a machine in general? The work which you release, work, divided by the heat you input, which is the heat you input is the energy you input to the system. And the work is the difference between hot minus cold. This will be give you 1 minus cold to hot. But if you use this ratio, then it becomes this formula. So at the end, well, this is an idealization. And these guys, ideally, they keep constant the temperature. That's why, for example, the engines, the machines, you need the gasoline for keeping some temperature in your engines for operating. No? Ideally, they keep, when you shut down the car becomes cold. But when you switch it on, the temperature of the engine increases until it reaches some temperature which is constant. So approximately what is happening here. In the nature, we have natural sources of heat and natural sinks of heat. Ideals, such that their temperature doesn't change so much. And I talked about that before. So you should know right now. Tell me one example of an ideal, a perfect source of heat or sink, because sometimes it's sink, sometimes it's source, such that their temperature doesn't change. Approximately, because it changed was with huh? Like what? The ocean, yeah. For example, the water of the ocean. So you mean the ocean? Yeah, the ocean. The ocean is an example. If I input heat to the ocean, I will not change the temperature. I don't have that power unless you are Superman. But that's Marvel. No, that's DC. Sorry. I mean, assuming you are not a superhero, if you input anything super hot in water in the ocean will not change the temperature. The same happened with the environment. The atmosphere, our environment doesn't change the temperature because of whatever we do. It has to be a cumulative effect in the long term, or it has to some appreciable effect. No? So anyway, coming back to this, tell me now that you know the efficiency of the Carnot cycle, what do you need to do for a machine to increase the efficiency? Based on these variables, based on this information you are seeing here. Who say me? You say me.
You have the ratio between the two heats at the top in relation to the total heat of the system. The relationship between the heats.
Yeah, that's the key point. It's the relationship between the heats, or in this case, the relationship between the temperatures. Because
so that it's
close to 1 or close to 1, the efficiency will go to 0, right?
no, plus one not.
If cold is near hot, this will be almost 0, no?
Oh no, I mean the heats divided by the total heat. That relationship is equal to 1.
Okay, that's what you mean. Well, looking at these variables, it will be equivalent to say the larger my source, the temperature of my source is, better, more efficient will be my engine, or the colder is the temperature of my sink. Then it will be much better in that sense. So because those are the variables I can control. No? Now, remember, let's review a thermodynamic cycle quickly for being a realistic case. You have a thermodynamic cycle like this. You have the heat, well, here, let's repeat here. The heat enters, expands something. But in this expansion, there is a cycle of expansion and then a cycle of compression. It's in that compression where the heat at the bottom is released. And that's why you cannot use the whole heat you receive, because you have to come back. Then it's impossible to construct a machine with a perpetual motion, which is operates taking advantage of the whole heat. This would violate the second law of thermodynamics. There are some theories about that, very well formulated. So this is something important. Now let's go to refrigeration, which is the opposite. But before going to refrigeration, this is the pressure volume diagram, but actually there is also there are other combinations of pressure, temperature. I will send to you those diagrams very well illustrated for you to have it. Usually the Carnot cycle, if you put in temperature, volume, for example, since the expansion is a constant temperature, I think will be something like this, on a square, something like this. It will be a square. It will be a square. So it expands, isothermal expansion from 1 to 2. Then, of course, some release of heat here, a constant volume. Then coming back, contraction, a constant temperature, and then increase a constant volume when you input the heat here. You input heat, and the heat goes out here. Okay, well, I will send you these illustrations in detail subsequently. But you should know that this is the ideal cycle, the Carnot cycle. This is the representation in pressure volume. And there are many thermodynamic cycles standard in textbooks. The Otto cycle, diesel cycle. There's a cycle called diesel, like the giant. No? In refrigeration, we don't use efficiency. We use something called coefficient of operation, actually. In this case, refrigeration, the water is entering to the system, and then you force to extract heat from the room, which is supposed to keep cold, to extract to the high temperature, right? Then, for example, you have the following. The following issue. This is, we are here, room. You want to keep the temperature at 15 degrees Celsius. Then for extracting heat from here, this has to be colder, let's say at 10 degrees. The machine has to work, has to input some work from here. Has to input some work for forcing this to happen. Then the heat goes from here to here. This is what is happening here. Then we are in this room. We are happy here. Then what happened? What happened when this comes? these guys, we elevate the temperature. And let's say that the environment has 35 degrees Celsius, then this guy here has to be like 40. Is the machine in the external has to be at a temperature larger, and it will emit heat. Then it will close here. This is an expansion here. This is a compressor, which made the air to increase the temperature for, and then the air come back here. And then it become cool, cool, and cool. Then cool air. This cycle we revised before. You remember? Well, this is what happened. Well, this cycle, the efficiency of the refrigeration cycles is measured by something called coefficient of operation, not efficiency, and is defined in this way. Is the heat which you release, this one, divided by the total work, which is the difference between the heats. This is the total work you input. So at the end, using again the ratio between the it's this perfect relationship, which is valid for perfect sources or perfect sinks. Then you obtain this formula. And something you should notice is the coefficient of operation has to be, for a good design and machine, has to be larger than 1. Has to be larger than 1. Otherwise, your machine is very bad design. So what do you have to do for increasing the coefficient of operation? Remember, the efficiencies are normally smaller than 1, but the coefficient of operation has to be larger than 1. So if I want to increase the performance of the refrigerator, what do I have to do? Hot, hot, cold. This is hot. This is the difference between hot and cold because it's the work. In a thermodynamic cycle, remember the work is the difference between heats. No? Difference between this and this gives you the work. There is no change of internal energy because it's a cycle and the change of internal energy in a cycle is 0. What?
Yeah. H. Or increase.
Well, ideally, if cold and hot are closer, of course, it will increase. Well, of course, this will never happen. And evidently, our coefficient of operation, well, still, if you design well the machine, it has to be. This is the idea. Of course, your coefficient of operation will be different for the real machine. No? With these thermodynamic cycles, we close the lessons, but let's go to this example. Unfortunately, the letters are quite small. I think let me see, how do you amplify this? I forgot how to amplify this thing, how to make it bigger. The 3 dots, yeah. This one. That's enough. Okay. This is an example of thermodynamic cycle problem. Is a Carnot engine has efficiency of 0.6 and the temperature of its cold reservoir is 300 Kelvin. What is the temperature of the hot reservoir? If the engine does 300 joules per cycle, how much heat is removed from the high temperature reservoir per cycle? How much heat is exhausted at low temperature reservoir? Blah, blah, blah. Well, anyway, they give you the efficiency of the Carnot cycle, 0.6. 1 minus, and they give you the temperature of the cold reservoir. So you can solve for the hot one. Because in the Carnot cycle, the efficiency is a function of the temperature. Later, I will share with you this example. The second question is, if the engine does 300 joules work per cycle, how much is removed. Remember that the work, well, you can use the efficiency because the efficiency is the work divided by the heat you input, no? Remember, you have the machine here, temperature height, temperature cold, you have work, then the heat flows in this direction, and you have this efficiency. The efficiency will be the work, which is the difference between QH minus QC, divided by the total energy you invest in the system. And the total energy you invest in the system is the hot heat, let's say. It sounds redundant, but the heat from the hot source, let's say. From the source is better because we know that this is the source and this is the sink. Then it's the heat coming from the source is the most accurate definition. You can do like this, but you could also do Q heat minus QC. It's valid also. It's valid. Or you could use the original formula and start again. It doesn't matter. Anyway, you have 300 joules of work, which is this difference, divided the efficiency, which is 0.6, and give you the Q heat, 500 joules. Solving here, this is not difficult, no? Q heat equal the work divided efficiency. And finally, how much heat is exhausted to the low temperature reservoir cycle? There is a heat exhausted here, which we know is 500 joules. We know that the work is 300 joules. It was 300? Yeah, the work is 300 joules, this one. 500 is what it comes original. So the difference gives you 300. So how much do you need here in the code? It will be 500 minus 200 is 300. So it will be 200. And actually, you don't even need to do it. You can do it mentally here. So you can see the work is the difference between the heat coming here minus the heat coming here. That's it. Okay? Excellent. Good. So now we have finished, we have closed the thermodynamic cycle. I will start then with fluids. We will advance with fluids because it's connected, it's more directly connected. For starting with fluids, I will switch on the light. This last 15 minutes will be a brief introduction and the historical motivation for this. So let me shut down this and let me switch on the light. Then I'll put it this way. Fluids, we will do hydrostatic first, and that will include buoyant force. And we will do Bernoulli after. Bernoulli, hydrostatic, special case of Bernoulli. Hydrostatic is a special, and you will see later why. And this has plenty of applications. Let's assume that you construct China or any country construct this kind of water containers. You have a river coming, a lake, and you want to contain the water of it with some artificial wall or something. Guess what? They have to take into account this. First is that if you make this wall and the water is contained here, this is water, you have to take into account that the pressure here is larger than here. So it means that your wall has to be highly resistant at the bottom. So that's why you will see these walls, in reality, they are designed like this. It's mostly like that. And the reason is the pressure here. Remember the pressure, the deeper you go, the pressure is like rho GH. Density, gravity, height. So the deeper height content, deeper, no? So it means the deeper you go, the higher will be the pressure. we will see that this is the case of hydrostatic. Interestingly, because the fluid is static, it's not moving, it means that each point, if I analyze one point here, this point is ideally in equilibrium. So it means for a point to be in equilibrium, what does it have to happen? The pressure has to go or to come from all the directions to this point. So in other words, when you are inside the waters very deep, you will feel in each point the pressure coming from multiple directions to that point. And the pressure on your feet will be larger than the pressure you feel on your head if you are standing. Well, if you are doing something strange, it's different. No? So this is hydrostatic. We will study this the next time, the next class. And this explains why, for example, the opposite happens when you are flying a plane. Let's assume you are in a plane, and you're flying. We are in the air here, the plane is flying. The air is a fluid. Imagine that the air is water. We are fishes moving on the water, but is the air already. Fishes moving in a fluid along a fluid called air, which has lower density than the water. The higher you go, the pressure will be less. The same as what happened when you enter to the waters of the ocean. In the ocean, the lower you go, the higher the pressure. The upper you go, the lower the pressure. With the air is the same. That's why when the planes are flying, what happened? First, they have to fly faster because there's lower density of the air. They have to keep some speed for keeping this buoyant force, which we will study why the planes fly in this class. And the second is that the cabin has to be pressurized for you to breathe, because otherwise you cannot breathe. Then, for example, what happened? Well, before asking that question, let me say something. When the plane takes off, the fuse, the engine, the plane expands. You don't see it, but it expands. It expands. And it contracts when it goes down. Expand, contract, expand. The material of the plane has to be designed for resisting this kind of expansion contraction. And I will tell you a secret. That's why those planes that are traveling short distances, like 30 minutes, 40 minutes, they have to be even more resistant to this kind of changes than the planes which are designed for long trips. When a plane is in long trip, doesn't suffer so continuous cycle of expansion and contraction. But for short flights, this happens. So this is an issue which the designers of materials have to take into account, for example. Then the cabin is pressurized. What happens if somebody is stupid enough to open the door of the plane, believing that it's like being in a car? Let's open the window. And it happens in a plane in Korea. You remember there was a news, genius, the guy who doesn't study physics. And that's why it's so important to study physics, because some guys don't underestimate physics, but those are the guys who open the doors of the planes when the planes are flying. The door of the plane open. What happened initially? If you are by chance unlucky crossing by that door, you will fly away. It will drag everything which is close to that door outside, until there is an equilibrium of pressures, internal and external pressure. When it happens, what happens? You cannot breathe. The mass will go down, breast, people shouted, tragedy, panic, until the pilot, what does he have to do? Put the plane down. Put the plane down until a certain height such that people can breathe, until you solve the problem and find some emergency place for landing, emergency landing, because unfortunately some guys, they believe that being in a plane is like being in a bus, and then this is an issue serious. Other applications of hydrostatic were many. Imagine in the past, when they didn't have the technology we have now in the past. Now imagine people were in a town here. They want to establish a town here. What is the basic of civilization? When you want to establish a civilization, what is the basic resource you need? The most basic one, water. They have to establish near a river. Well, ideally, the town is below the river. And the reason is the difference in pressure, because it will allow you to construct canals, able to bring the water to the town. And that's what happened in the past. They only use the strangulation valve, which you open and close, but they try to establish the town at the levels lower than the location of river and lakes. Very important, eh? Physics is useless? No, it's very useful actually for your daily life. Even for your daily life. I mean, sometimes people make stupid errors is because they didn't study physics. No, serious. Even open the plane of the solar plane is one of those errors, no? Or using the wrong logic for a sequence of events they should do, for example. This is one thing. The other, we will see in your class, next class, we will study buoyant force and the Archimedes principle. Buoyant force is when you have, for example, the ice. This is water. I put an ice here. There is an equilibrium between the force of gravity, which the ice feel, and a buoyant force, which is going up. This buoyant force is equal to the weight of the fluid displaced by the object. In other words, if I want to make the equilibrium of this, will be mass gravity of the ice equal the mass of this water displaced, which will be this volume multiplied by density times gravity. This equilibrium, and then with this, because this is density volume displaced, density of the ice, no, density of the water, sorry. You can know what's the percentage. We will learn how to calculate the percentage of volume below the water of the ices, and you will be surprised about the icebergs about them. Then you will not underestimate the icebergs next time you see them. No, not even watching the external side, the external part, you will underestimate them. No, this is something. Archimedes principle is a different issue. It has applications, and you have used it before. Hydraulic forces, when you try to put the car up to changing the wheel, you use some hydraulic forces, no? Or when there are some cameras elevating the cars, then, for example, you have some area here. You have a fluid here. And then, of course, you transmit a small force in one side, and it will generate a huge force in the other, transmitting that force through a fluid. That has plenty of applications, and applications in the daily life, and you can even apply in some of your experiments or anything. No? So these kind of things we will learn in the next class, and finally we will close the part of fluids with Bernoulli. Bernoulli is conservation of energy. It's an extension of the first law of thermodynamics, actually. But there are some issues. There is an energy due to pressure. There is an energy due to gravity, which is the potential. And there is kinetic energy. This is constant when a fluid is moving. And this explains why the planes fly, for example. Why the planes fly, or why the Formula One cars, they don't fly, the opposite. Because actually Formula One racing car is an inversion of the wing of a plane. They use the same principle in the opposite direction. So the force is putting the car down so that you will not fly away. But if you abuse on that, then it's a lot of traction and make the car slower. That's why the pilots, they have to be smart and tell to the mechanics, hey, I want this wing like this in this angle. So I mean, they need to know a little bit of physics, a little bit, the pilots. So Well, let's talk about the planes. Again, plane. We will calculate something. And this calculation will amaze you. We will calculate what is the velocity that a plane has to keep in order to fly. Based on its weight, we will find in Google the weight of a plane. Tons. Plus the passengers. But even without the passengers, it's already heavy. And we will see what is the speed. The plane based on the design of the wing. Because what happened is the following. When the planes fly, they have to keep some velocity. What happens if they lost the engines and the plane cannot continue keeping that velocity due to the friction? It starts to fall, but why? Because there will not be difference between the velocity of the air on the top and the velocity of the air of the bottom of the wing. When you see this wing, the air is flowing bottom, and there is air flowing on the top, on the bottom. Upper and lower flow of air. Where do you think the air is faster when it's flying? Upper or lower? I think the first response was correct. I just look like that on purpose. But let's say, don't be scared when I look like that. It's just a question. Yeah, it has to be faster on the upper side. Why? Bernoulli. If the kinetic energy is large, the pressure will be lower. So you need low pressure on the upper side, and you need high pressure on the lower side. So on the lower side, the velocity will be lower. You will have more pressure, and that the difference, the gradient of pressure will be pointing upward. So it means the plane will fly. Who were the first guys who could fly a plane? This is some brothers. The Wright brothers. Yeah, the Wright brothers. They did a toy, almost like a toy plane. No, it's in the Hong Kong airport exposed. No, the replica of that plane. Imagine they just flew like a few meters like this. Well, imagine that. Those guys were curious guys, just like you, doing experiments, being a little asking themselves questions, and they developed what today is so useful. No? And in that time, what happened in that time? Somebody tell them, that's useless. That doesn't give you money. What will be our society right now? Then wonder yourself about that. So when you see some physics or so, we have to show some respect. Scientists deserve respect. No? That's important. The universities also have to respect the scientists, no? Because those guys have the source of the knowledge which keep the society. So then it's nothing against anybody. It's just I didn't say anything against then we will learn this, we will learn the other things, and I think with this I want to close this lesson, and I will send you the videos as usual. It's useful, these videos. You find it for reviewing the class. It's okay? Okay.